Imagine a newly created Bitcoin transaction. Before it becomes official, it exists in an unconfirmed digital void called the mempool. It's a space where data packets wait for someone to process them and etch them into history. Without a central bank or a CEO to officially stamp these movements, the network faces a significant risk: the double spend. This is where a user attempts to spend the exact same digital coin twice before the ledger can update. Welcome to the Foundry by Forge College. Today, we are looking at the mechanics of Bitcoin mining, the process that solves the double spend problem and keeps the network alive. Mining is the process of grabbing those floating transactions, locking them into an ordered history, and securing them behind a wall of mathematics. To understand how this works, we can look at the three distinct responsibilities a miner handles simultaneously: managing the ledger's records, performing the raw computational labor to secure them, and competing in a high-stakes global lottery. This is a delicate, intentional balancing act of economics, mechanics, and probability. It is the specific machinery that replaces the need for a central authority. The process begins with the logic of a profit-driven record keeper. Miners dedicate massive amounts of capital and electricity to the network, and they do so with the expectation of a return on that investment. This diagram shows how miners sift through the mempool. Because every Bitcoin block has limited space, miners strategically select transactions with the highest attached fees. They want to pack as much value as possible into every block they process. At the very top of this block, the miner adds a unique record called the coinbase transaction. This is where they claim their payment, a reward of brand new Bitcoin, the block subsidy, plus all those collected fees from the transactions below. But that self-written check remains invalid until the rest of the network accepts the block. To earn that acceptance, the miner must move from administration to raw physical work. This alignment of selfish economic goals ensures the network remains efficient. By chasing higher fees, miners naturally prioritize the transactions that users value the most. Once the transactions are selected, the record keeper's data is compressed into a single digital fingerprint called a Merkle root. And now the heavy computational labor begins. This is proof of work in action. The miner combines the block data with a random number, a nonce, and runs it through an algorithm called double SHA-256. They are looking for a specific result, a hash that falls below a target line set by the network. If it doesn't fit, they change the random number and try again, millions of times a second. It's the digital equivalent of trying to crack a combination lock by spinning the dials as fast as possible. There is no clever shortcut. The only way to find the answer is through a massive expenditure of electricity and specialized hardware. This creates a vital imbalance. It is incredibly difficult to find the solution, but it takes less than a second for every other computer on the network to verify that the answer is correct. Getting into the weeds of these cryptographic algorithms is a core part of what students practice throughout the Forge College curriculum. This process converts real-world energy into verifiable digital security. It makes tampering with the ledger physically and financially expensive. At a global scale, this becomes a massive distributed race. Millions of computers are attempting to find that valid hash simultaneously. Success is probabilistic. Every single hash attempt is a lottery ticket, and owning more powerful hardware simply means you hold more tickets for the next block. To manage the high cost and rare wins, many miners join pools, grouping their tickets together and splitting the winnings to ensure a more predictable income. Sometimes two miners find a solution at nearly the exact same time. They both broadcast their work, creating a temporary fork where the network has two competing versions of the truth. The network resolves this using Nakamoto consensus. All participants eventually follow the chain that proves the most cumulative work, the longest chain. The shorter branch is orphaned, and its transactions are sent back to the mempool to wait for the next block. This probabilistic model ensures decentralized competition and establishes a single mathematical truth that everyone can agree on. When you combine these three roles, an attack on the network becomes nearly impossible. To rewrite history, someone would have to outwork the labor, outwin the lottery, and walk away from the honest rewards they could have earned instead. The economy as lining is designed to shift over time. As the block subsidy, the new Bitcoin, is cut in half every few years, transaction fees will take over as the primary incentive that keeps the miners running. This creates finality for the user. Every new block added on top of your transaction acts as another layer of a mathematical shield, making it exponentially harder for anyone to change your financial past. This translation of economic signals into security is what makes the network thrive. In our next lesson, we'll look inside the block header itself to see the exact data fields miners manipulate to find these solutions. To learn more about consensus and join the learning community, visit us at forge.college. We'll see you in the next lesson.